Of these three predictions, this one here is the only one that holds true. Yes, indeed, if we plot the current versus the intensity, more intensity does result in more current. However, there is no correlation between the maximum kinetic energy and the intensity. For a given frequency, if I plot the kinetic energy versus intensity, it's totally level. Also, this time is entirely wrong. Whatever the intensity of incoming radiation, the current starts almost immediately and then stays at a constant level. So we don't have any buildup of energy. As soon as light hits it, electrons start getting knocked off. But perhaps the most surprising is what happens when we plot the maximum kinetic energy versus the frequency. We would expect no correlation whatsoever. And yet, we get a linear relationship. What we find is that the maximum kinetic energy is equal to some constant times the frequency plus some other constant. Actually, if I'm going to plot it this way, I should make this a minus. We actually normally plot it slightly different. All right, but here's the key thing. If I don't get a high enough frequency, electrons are not knocked out at all, no matter how intense I make the light. When I reach that minimum frequency, electrons will be knocked out, whether I use intense light or very, very dim light. Intense light will give me more electrons, but dim light will still give me some. As the frequency increases, the energy, the maximum kinetic energy or the maximum stopping potential, also increases. So somehow or another, the energy is dependent on the frequency. What Einstein did that won him his Nobel Prize was to take a look at this formula that Planck had and basically take it seriously. Planck had thought that this was a calculational tool, that by imagining that light was absorbed and emitted in units proportional to the frequency, he could fit the radiation curve of blackbody radiation. Einstein said, let's treat that as actual packets of light energy known as photons, and that each one has an energy proportional to the frequency times Planck's constant, where Planck's constant was the same one Planck himself had figured out, 6.63 times 10 to the negative 34 joule seconds, or 4.14 times 10 to the negative 15 electron volt seconds. Then all Einstein had to say is that this energy goes into two places. First off, that energy has to be some minimum amount to knock it out of the metal. He called that the work function. So that was the energy necessary to knock it out of the metal. And the rest went into the kinetic energy of the electrons. It turns out that this formula fits this data very nicely. It became known as the photoelectric equation. And like I said, this is what won Einstein his Nobel Prize. It seems like a very simple equation. The slope here of this line was exactly Planck's constant, and the work function here was a constant for any metal, but for different metals would give different values. As a result, it took different minimum frequencies to knock electrons out of cesium, potassium, sodium, or lithium, or any other metal you might try. But the most important part of this result was the fact that we had to take seriously the idea that light came in little bundles known as photons. This was a big step because there had been a long fight over whether light was particles or waves, and because it showed diffraction properties, waves won. And yet now we had a new experiment that could only be explained in terms of particle properties. Okay, so we have this increase of kinetic energy with frequency. We can also explain this fact that the intensity jumps immediately as soon as light is turned on from the particle point of view, the photon point of view. As soon as any one photon hits an electron, it delivers all of its energy to that one electron. So as a result, we don't need a slow buildup. The current is started immediately.